Good morning. It's time to start the second day of the workshop, or third day if you count the tutorials. It's a great pleasure and honor to introduce Dr. Marina Krotofil, who's currently a lead cybersecurity researcher at the Honeywell Cybersecurity Lab in the US. Previously, she worked as a senior security consultant at the European Network for Cybersecurity in the Netherlands, and her research over the last few years has focused on discovering unique attack vectors, design vulnerabilities, engineering damage scenarios. Actually, a lot of very interesting work. Both I and my group have been following Marina's work over the years, and she has very interesting insights on both academia and industry as well. So she's a frequent speaker in leading security events like Black Hat, DEF CON, CCC, Zero Nights, and so on. The videos are online. I encourage you to go and watch. Actually, it's a live version today, but there are also YouTube videos you can see. So with that, the floor is yours.
Thank you so much. Wow, what the introduction. Actually, the honor to be here is mine. I really very much enjoy all the talk yesterday, and the quality of the research is so high. And actually, it was I'm glad that my talk is on the second day, because I could actually estimate what is the knowledge in the audience, and it seems we're operating on the same terms like sensor signals, because you have them in the image processing, I have them in my field. So that makes our life it's much easier, and secondly, it's always a pleasure to give a talk in the academia, because people are extremely smart, they know the methods, whereas if you go to the industry, people already forgetting what they learned, and it could be difficult to explain what entropy is and why do you compute the entropy. So it will be a huge pleasure to deliver my talk in here. So I will talk today about challenges of the forensics in the industrial control systems. I named these attacks like man in the skater. So what are industrial control systems? In a nutshell, it is a bunch of computers which is hooked up together to control operations of the physical application, which could be power generation, food production, producing chemicals, and so on. And so it typically consists of two sets of networks, which is one is a corporate LAN or enterprise LAN, which is called information technology. And there is another network, which is called process control network or industrial network, which is called, so it is the same set of computers. They look the same, they perform the same function, but because their main goal is to support operations, suddenly this technology is already called, those computers called information technology, or operational technology. So, and it's very important to understand that it's only in the purpose of which they serve, which makes them give them different names. So, and the purpose of the attacker, so it's very important to understand that the purpose of the attacker not just to hack into the system and be in there, but to actually cause a tangible impact. So in mass media, the majority of the hype and most of their actually also research interest is concentrated on the preventing attacker from, or researching how the attacker would get into the control network. But the point is that the most interesting to understand how the attacker would actually cause physical damage, because eventually this is his effect, not just to be there, his entire purpose. So, and this is where the public knowledge falls short. There is hardly any knowledge of how the attacker, about the attacker strategies and technique, how to cause those that tangible impact. That could be not necessarily physical damage of the equipment, but it could be just basically making a product unusable, making operation more productive, less efficient, causing you maintenance, troubleshooting problems and so on, basically making you running around. So this is what basically, this is who I am. This is what I've been studying in the last 5 to 6 years. It took me around 3 years to become competent in that field, and after I've become gained all the necessary knowledge, then I started really doing some work. And if you look at my research interest, it sounds like, oh my God, how is it possible to do all of that in this field? Very easy, because the research in this field non-existent, so you can basically, it doesn't matter which research questions you will pick, you will find something new. So it's actually it's an easy field in that sense, but it's difficult to, of course, because you're alone, so it's difficult to collaborate, it's difficult to ask for advice. So I discovered several unique entry points into the system because the attacker, in most cases, the attacker won't come through the firewall. I've been studying extensively attack strategies, and this is what is like mostly my current attack, my current interest, and I'm publishing a lot of works in this, like exactly in the attacker strategies. I discovered several novel attack vectors which do not exist in IT domain and which cannot be actually defended with traditional IT security methods. And once I identified those attack vectors, I started like basically engineering attack instances because like if you know, like if it's, for example, buffer overflows, there are so many ways how you can exploit it. So those are attack instances. One of my recent passions was also discovering design bugs. So that is something which would require re-engineer the entire system. So that's in contrast to the, like, for example, application bug, which you can issue the patch. For example, and regarding these design bugs, I've been recently in contact with industrial control system CERT, which is like the global CERT is like American CERT is currently like global CERT, and we've realized that basically reporting design bugs is completely different from reporting like implementation bugs, and they will start an entire new branch how we would be able to report design bugs. And also I've done basically 2 applications when I engineered the complete chain, attack kill chain, basically from entry to finalizing the malicious payload. Those were huge pieces of work. I did it in the context of chemical plants and traffic light systems. But those are really like very large scale, more than a year projects. So, and basically what I'm doing all of this because, yeah, we cannot design defenses if you don't know offenses. So basically I do this to develop risk assessment like approaches, methodologies, and to develop operations aware security control and defenses. And I was lucky enough to be basically integrated into both academic, industrial, and hacking communities, which basically also allowed me to expose to a large variety of issues and also to collaborate with both hacking community, with industry, and academia. So, and what I discovered is that this field is very interesting because every assumption, everything, my expectation, which I saw that like, oh, if I will exploit like these systems in this way, this is what the outcome, and it was completely different. So, but like, I was wrong so many times, and it's really fascinating to read mass media, especially newspapers, when they describe how the hackers would cause havoc or Cybergeddon. And I just want to laugh because it's just like, it's all wrong. So one of the main questions, especially, for example, now when I'm Honeywell, our customers are asking me, like, but really, are there attacks in this SCADA? And the problem is that the accident data held very tight, and in most cases they are classified, or the investigators are tied by NDA and legal agreements. And there is no trust. There is very little sharing, as much as there is many initiatives going globally to establish this information sharing. It's still not there. Also. There is no forensic tools or any tools to investigate, to monitor, and to look into the control systems in networks. So basically, the visibility in the process control network is equal to 0. We can't see in there. And unfortunately, the participation of volunteers like academia or freelancing researchers or just enthusiasts is very limited because it's very difficult to buy this equipment. Sometimes you just simply cannot purchase the equipment because the vendor won't sell it to you. It's also very expensive. So basically, even if it's difficult to afford it, even for the universities. And also the problem is that because all the equipment is so non-homogeneous, your efforts do not scale. If you develop a specific approach or tool for one device, it won't work for anything else. So, and now we have this vicious circle that because there is no discovered attacks, there is no demand for forensic tools. And because there is no forensic tools, we cannot discover any attacks. So how do we break it? And to be honest, I don't have answer right now. I keep running around screaming we need to start for developing those tools and capabilities, but the customer, so basically industry cannot develop what customer don't want because they're business driven. We have to make profit. So basically it's us, academia, who has to start maybe making some efforts, and this is why this talk is about, to outline you what we need to do. So before I go into the explain the challenges which we have in this forensic investigation in the systems, I'll give you SCADA 101. And basically, I will show you how I and my colleagues will look at the process control system security. So what is process automation? Probably, I know that you will be able to understand and you probably know it better than me, but to make sure that we're all on the same page. So basically, the easiest case is a thermostat. So we used to have, like, even still in my childhood, we used to make it manually to adjust the furnace in the boiler, but now we have all the thermostats. So we set it for a specific temperature, and we have a sensor which measures the temperature, and then it automatically controls the valve in the furnace. So this is called, so basically the system, the control system works in the control loop. So you have physical process, you have sensor which measures the temperature. The sensor signal goes into the control system, which does some magic and eventually computes command to the actuator. It could be, for example, valve in the furnace, so which we open the more gas or less gas, and it goes in the loop. So in the large-scale operations, the control logic gets a little bit more complex, so this thermostat won't be enough. So we need something more bigger, more reliable, and in most cases, this piece of equipment, of control equipment, is called programmable logic controller. So this is how, like on the real plant floor, the sensors and actuators would look like. This is a photo of the test bed, fantastic test bed in Singapore. So how the PLC works, it takes inputs from the sensors, it runs the logics, and then it copies the computed numbers to the, like, commands to the actuators. So what is control logic? Control logic is programmed graphically most of the time. It's a Boolean logic. It's like yes and no or no proposition. And it defines what should not happen, under which conditions, in which sequence, at what time. So for example, like within the same PLC, could be like if input 1 and input 2 like positive, then do something in input 6. Or also logic could be inter-PLC. So basically if like one PL controller is controlling one valve in one tank and another PLC controlling another valve in another tank. So one of the most difficult tasks for the attacker would be to understand this relationship between logic and points. Points, so basically all control systems work on so-called points abstraction. So everything what can be measured or controlled is a point. So typically a plant would have like more than 10,000 points. So, and the attacker has to, every point has a tag, which is called the variable name. That will be stored in the PLC. So once the attacker will, like for example, he will steal the process diagram and he will identify pump of interest, he will need to like basically go into the networks, look for the traffic and find out in which PLC that logic, that variable will be, pump will be stored, find it in the logics. So basically, which eventually he will be able to send commands to the plant floor. But that's not all. So basically, the logic only determines like logic of the events, like sequence. But we also have a control algorithm which actually used to compute the output to the actuator. So it takes the input from the control logic, and then it uses this funny equation to compute the output to the actuators. So this is basically, so PID, proportional integral derivative, is the most widely used control algorithm on the planet Earth. It's already pre-programmed in all the controllers. And at this point, whenever I give a talk, this is where all IT people already just like, okay, I'm not interested at all. But the point is that understanding the tuning, understanding tuning of the control loop and understanding how to destabilize is actually the key to the cyber-physical hacking. Without understanding this, so basically, if you want even to make drone falling out of the sky, you need to understand the control loops and think how to destabilize them so that eventually it will lose the power and fall down. So PLC unfortunately cannot do it all alone because it doesn't have like the complete picture in the plant. It does not have timing trends. So therefore we have human operators who monitor the process all year round. And the most critical task of the operators is to resolve alarms. So typically there could be millions of alarms even per hour because they're all programmed, but humans cannot resolve more than 6 alarms per hour. So you will be suppressing all alarms, which basically does not pose immediate danger to the process. And they will be only dealing with those issues which really require immediate attention. So modern control system became already huge and large. So this is a structure of the Honeywell distributed control system called Experian. So here we still have sensors and controllers, but all of this is needed. Those are basically information systems which process the data measured by the sensors and take all the smart decisions and push down to the actuator some control commands. It's really got extremely large. Therefore, it's actually called a knowledge system. So, and if, what is again, like IT people don't like knowing basically, or where they lose interest is that the most crucial component of the, basically why do we need even those IT systems or computers? It's only to deal actually with process data which are measured by sensors. And the point is that why do we need that many systems is because actually the sensory data are never usable immediately. So we need a lot of electrical circuits, applications, and devices to actually transform and convert those data into something that can be usable and from which we could extract information about the process. Therefore, the data is constantly conditioned, converted in different formats and aggregated together, transformed. That's why then we actually have this big data analysis and so on. And one of the, I'll skip this one. So when computer integrated manufacturing was introduced in the 1970s, so basically data became the most essential component of in the process automation. And actually, so once this is where the IT systems come in place, so the goal was to establish the architecture of the process control system in such a way that we have transparent data flows which represent the hierarchical data processing. So that architecture of the network got a name as automation pyramid. So here at the bottom, we still have our like sensors and actuators. And at the lowest level of this automation pyramid, the equipment operates on the raw data. So we hardly do any processing, but this data is also not passed to this level of the, like basically to higher levels of the systems. So operator is already operating the process based on the information. We start extracting information and send it to the operator. So therefore, we have here control loops which operate on milliseconds, and here we have already system which operate in a second. So this is very important when you design the network. So for example, if there is a requirement to pass for the data to be delivered in the real time, you cannot send those data, for example, via the Ethernet switch. And again, this is all very important data also for the attacker, because if he will be able to cause damage at the lowest level, there is no actually time to react. So just to explain, like give a fun example of the impact of data processing on the on the operation, there was an accident. There was a line of nuclear plants which were all built absolutely identically. Let's take two of them. So so eventually one plant was experienced a catastrophic breakdown. So basically, before the operations, they've noticed that one plant had a flow-induced vibration issue of the equipment and another did not. And they could not understand why. And eventually, so that plant which did not have a vibration that was operated at full load, and eventually it led to the breakdown. And when they started to investigate, it turned out that the vibration issue was monitored, like it showed itself as a resonant frequency in a specific sensor signals. But the guy who was maintaining that piece of equipment, he was kind of disturbed by the noise of the signal. He's just like, I will just change the cutoff frequency. I will filter out those high frequencies. And with that, the operators lost complete visibility into the vibration issue. So data processing is also one of the attack vectors, because by simply changing the configuration of the signal, the attacker can already blind the operators and the equipment about issues, about true state of the process. So in a nutshell, cyber-physical hacking consists of two tasks: is manipulating the process, and secondly is preventing response. Because control system always, and humans always respond, you have to deal with that. So you basically have to deal with operators, and you have to deal with the control system, including safety. And for example, so basically, especially in case of, I will not go into details here, but it's always interesting to understand when you have to prevent response and when not, because this is sometimes required, we will see on the next slide, that's required to actually create forensic footprint in the network. So typically the attacker would want to maintain control over the, basically, I'm sorry for that. For example, if the damage to the equipment is instantaneous, you don't even need to bother to prevent response either from operator or safety system, because the breakage would happen too fast. And sometimes, in one of my attack scenarios, I only needed to blind the operator because I did not trigger, I designed the attacks which would not trigger alarms. They would not exceed operational limits or safety limits. So I only needed to actually blind the operator. And in certain cases, you have to basically blind or prevent response from all of the control systems and operator. So why do we need to hide, or basically, why do we need to blind or prevent the response? The point is that one cannot hide physical consequences by simply altering log files, because if something is broken or burning, it is noticeable. So therefore, for attack persistence, or basically to avoid the attribution of the damage to the attack causes, you have to make them believe that the cause of the attack is anything else rather than a hack in the system. So for example, one of the most common breakage reasons in power sector are squirrels. So if you broke a substation, then at least make sure to put a dead squirrel in it, in there. So, and this is where we already come in a little bit into the techniques of creating forensic footprints in the industrial control systems. Again, this is very different from the IT systems. So, for example, if you would time the attack to the specific employee shift or maintenance work, then the employee will be investigated rather than the process. And you can do the same trick with whenever the set point is changed, whenever you change the supply of raw materials or new equipment is introduced and so on. And this is because designing attacks on the industrial control systems is such laborious work. You would really take a time to wait for those rare events and not basically the attacker has time. So basically, like one of the scenarios which I actually designed and I implemented. So for example, I picked several ways how the temperature in the reactor could be increased. Then, like for example, you wait to the scheduled recalibration of the temperature sensor in the reactor. Then you perform first attack. You wait, for example, when the maintenance guy will be screamed at and he will be sent like, go recalibrate your sensor. Then you play the second attack and so on until they all get tired and they will start investigating the reactor. And even then, I still was, then if the forensic people will start investigating the reactor, there are a lot of techniques how you can basically mislead them about true causes of what's happening with the reactor. So what are the challenges? So there's basically, this is how our world looks like, including for offense and defense. So what are the current challenges in the forensic investigations? So basically, this is like a common knowledge, you probably know all of that, but there are we have basically issues with all of the 3 points. Basically, at the moment, as you've seen, this like control system is large. There are so many applications. There are so many systems. At the moment, we don't have knowledge where and which data to collect. Secondly, we almost do not, let's say we have limited understanding what are the requirements to the data collections and what are the constraints. So, and I will explain all of these points in details in the next slides. And secondly, with which methods and tools, which actually at the moment non-existent. So one of the main challenges of the like performing forensic in the industrial control systems world or at the plant floor is that there is a really absolutely humongous variety of equipment and protocol for humongous number of purposes. And every piece of equipment, so basically every piece of equipment or type of equipment from different vendors, they will be already different and proprietary. Not only that we have equipment for different purposes, but also from a very large variety of vendors. And that equipment and protocols will be different in in a million different ways, like age of equipment, hardware design, firmware design, programming languages, like for example, the way how you program the PLC, compilers, functionality, features, data formats, cryptographic primitives, available logs, and so on. Basically creating, being expert in performing forensic investigation on all of the pieces of equipment is impossible. You cannot even create a lab in which you would train your personnel to do those tasks because you simply cannot purchase that equipment. And it might be the case that even through the entire of your career, you might like basically meet each piece of equipment just once. And once you stand in front of that equipment, you don't know what to do with it. And the problem is also that even operating this equipment without vendor support is almost impossible. So this is why we have all of those remote connections right into the pieces of equipment, and this is where actually the attacker gets in, because we always need support, because actually, because majority of this, this is a really large problem that all the vendors want to keep the proprietary nature. Basically, they want to keep us blind because they want to prevent us from understanding the equipment. So we basically like locked into the support of the operators, of the vendors of the equipment. So what I can do, not really much, except just celebrating the diversity. So now let's talk about now we understand, so basically, so the variety of equipment, that is already a lot. Now, the problem is that, as you can see, the equipment operates on milliseconds and seconds of time. And although it is, there is a gradations like hard time and soft time, it still means deviations like in the milliseconds. So sometimes you like hard time, that would be nanoseconds, and soft time, real time, would be milliseconds, which is not really helpful. Deviation from the real time is unacceptable, because that will, whenever the process values or control commands are not arriving on time, you destabilize control loop and process fails. So deviation from real time is absolutely unacceptable. Downtime is unacceptable. So therefore, a lot of equipment, when you will try to collect forensic data from the equipment, it requires a shutdown. This is unacceptable. So for those equipments which cannot be queried for example, for volatile memory without stoppage, you cannot collect forensic data. And even that equipment which, like, for example, you can retrieve certain like data from the equipment without stopping it, it still cause threat to the availability. Therefore, you typically would have to have a testing equipment in the lab, try and see how the equipment behaves when you try to retrieve forensic data, and then only retrieve forensic data. As you can see, that will introduce a huge delay until you can get the forensic data from the equipment after the accident. Also, simultaneous collection of data may strain the network, because majority of the protocols and majority of the bandwidth in the control networks is very narrow, and it's almost always already full with control data. So you have very limited additional net bandwidth to send the forensic data. And therefore that can cause transmissions delay, and again that will violate the real-time requirement. So therefore you may need to collect the data device by device in a sequence. There is lack of documentation, as I already said. The vendor wants to keep their proprietary rights for the equipment. Therefore, in the manual, you will only see how to operate the piece of equipment for basically operational purposes, but not how you can dump the memory or firmware or collect any logs. In many cases, there will not be even, I've been in a situation when we've been performing forensic investigations, and the vendor would refuse even to provide such information, how you could retrieve data from the equipment, because nope, for intellectual property, I'm not allowed to do that. I'm not allowed to explain you that. Also, there is a lack of domain knowledge, because different attacks leave different traces behind, and because there is very little knowledge about how the attack would look on the piece of device, you're really unaware which data to collect from the device, which will allow you to, to understand that something has happened on the device. And also, as I explained, so sometimes you will need some time to understand how you collect forensic evidence from the device. And if you, for example, in 2 days I already know how to dump the volatile memory, but that volatile memory, it's real-time data, which is already obsolete and might not be actually useful to you anymore. And another problem, which is, and I really like the talk of two ladies who've been speaking about forensic on the embedded systems on the context of the gaming console, is the problem is that the forensic on the embedded systems is non-existent. They really nicely outline that there is no techniques, no tools, no understanding. We literally know almost nothing about that. So here's your device, find the hacker. So what you have to do, you have to get the firmware from the device. In most cases, again, it might not be even possible because the vendor already locked the JTAG port and so on. Then you need to understand the environment, basically how the device firmware was programmed, how it was compiled, and so on, so that you can understand which are natural commands or basically sequences of the assembly code on the device and which are not. Then you have to compare that to known good and reverse engineer the difference. There are only few people really on the planet right now who can really do that. And the challenge is that the attacks are really increasingly moving into the lower and lower into the embedded system. So 15 years ago or even 10 years ago, the majority of the attacks were happening in the communication infrastructure, but also because we know how to prevent those. We know how to detect man in the middle or ARP spoofing and so on. So the attacks slowly started moving into the control equipment and deeper and deeper within the control equipment. So from software logic, which is again, we more or less know how to understand and protect, the attackers moved into the manipulation of data directly in the memory of the controllers. And the recent advances are already manipulating data on the microcontroller of the equipment, either sensors or controllers, where we absolutely, not only we don't have defenses, we don't know even how to defend yet. And this is a problem that which we know in the IT system. So as soon as security protections are introduced at some level of computer architecture abstraction, the attackers always go one level down. And again, there is a problem. We don't have tools. So will we find the attacker? We won't. Are they attackers? We don't know. And there is a problem. So this is now where the comfortable place for the attackers to be. And I've been working extensively with the guys trying to exploit the system at the lower levels of the industrial control systems. So basically, we found a lot of ways how we can actually enter industrial control systems already. For example, you can, there have been a series of attacks when firmware of the transmitters, like basically sensors, were infected at the vendor page. Then they were uploaded by the operators and loaded into the sensors. So basically, you now can, in the next slide, you will see several attack instances when we basically actually design attacks when you can enter at the lowest level of industrial control systems and execute the entire attack there without ever reaching traditional IT systems at the higher levels of the architectures. And this is where, again, we don't even have visibility or network monitoring tools for this specific, for control networks. Another problem is that, the cause and effect in the industrial control systems is, or any cyber physical system or in distributed system, are their distance, not only in time that the causes, the system will react later, but also in space. For example, if you look here, this is one of the chemical plants I've been studying. This is vinyl acetate plant. So this is a case when the attacker was increasing temperature in the reactor. And the problem is that even if we suppress alarm here, so that the operator or safety system won't notice, we can suppress the alarm as a fact. But the physics will propagate further, and it will cause alarm in this system and eventually safety shutdown in here. So the attacker actually will have to, because all of these parts, it looks like a small diagram, but in reality, this, basically it could be distance 1 kilometer from this part of the process to this part of the process. So the point is that the attacker, oh, yes, it's on the slide. The attacker will have to basically to decouple the payload and basically implant it in several parts of the plant. And because the attacker already has its attack scenario, but forensic investigators, it's very difficult to predict. So basically, maybe I found one payload in here, but where else could be in other parts of the payload? Obfuscation techniques. So this is one of the, I have very good friends who investigate lots of malware. This is one of those recent examples when this is actually malware from this year, where you distribute the code in code which looks normal and harmless, and then eventually you assemble it in specific commands. So similarly, you need to come up with obfuscation techniques in the industrial control systems. And again, without understanding how those obfuscation techniques look like, it's very difficult to perform forensic investigation. What you could do, for example, one of the, what I've done in my, again, research career, for example, you have to destroy the relationship between process data. Because the attacker, when you perform forensic investigation, you will try to do the root cause analysis, look, oh, this happened first and then probably this is the reason. So if you destroy those relationships in time, then there won't be correlations anymore. And In my case, what I did, I simply changed the sampling frequency on the signal of the signals, and once it is smoothed and become shifted in time and uncorrelated to the signals. So it will be difficult to establish the timeline of what has happened first. So maybe my, okay. Okay. All right. So you can remove attack traces, like, for example, spikes and oscillations, by filtering or spoofing. So, for example, by simply changing, like, for example, filtering out the high frequencies, you can actually hide the oscillations. You can make data unusable, basically irrelevant to the process. You can mislead forensic investigator by preventing them from determining what is actually happening. It's just like, for example, you can cause false alarms. This is very popular techniques. And one of my favorite is alarm floods. So the problem is that, like, it's very easy to actually destabilize a process, that everything become anomalous, and you have an avalanche of alarms. So everything is red on the operator screen, and there is and once you will start looking at the, like, login servers, like, oh, what was happening, and you cannot determine what is more critical, less critical, and what has happened first, because you simply have 1 million of alarms. And as I presented already earlier, you can craft forensic footprint, making them believing in that, for example, the event is happening because of the bad weather and so on. So basically, in terms of cyber-physical systems, I've tried already so many things, and there is still so many things possible. It's just like really a delicious area of research. But again, without understanding how the attacker would be hiding their traces, it's very difficult, again, to perform forensic investigation. It's also difficult. So another problem which I seen is it's very difficult to interpret network traces. So currently there is several startups which start introducing solutions for monitoring process control networks. But the problem is that, for example, it's very difficult to tell apart poor engineering practices and malicious actions. For example, in one of the plans which we've seen that instead of, like, querying specific memory locations, the engineers would be dumping the entire memory of the PLC, send it to the upper layers, and it extracts needed memory, like, readings in the DCS, in the distributed control system. And it's very difficult to tell apart, is it a bad engineering practice, or is it the attacker is dumping memory of the PLC? Or there would be systems which randomly address some random addresses in the PLC. Again, it's very difficult to understand. Is this bad practice, or is it a reconnaissance that the attacker is looking like what is available in the memory? So, and again, the reason for this behavior as bad engineering practices is that because when the plant is commissioned, it doesn't function. You start tuning and making it efficient. And this is where you invite the multiple subcontractors, consultants, and this is when you start having fix on the fix, workaround on workaround. And even if you will talk to them like, do you really dump a memory? And they would say, like, I don't know. Who can ask? We don't know who've done it and when. So it's very difficult to really perform interpretation of the network traces. So to start with, to be able to actually perform, like, reasonable forensic analysis of the, on the network, we first need really to fix the control networks and formulate the good engineering practices which will be standardized, and then we would know which is, like, malice and what is misconfig. The other problem is that for forensic investigations, again, you really have to trace, for example, if you know to be able to trace a specific data flow into in order to investigate it. And the data flows from sensor to the end system are typically unavailable, and very often because the vendors would not provide this information for intellectual property reasons. So for example, I've been scoping a pen test in a power, it's large power distribution systems. And we've been asking okay, we need the network diagrams, we need this and that. And then I requested the data flow diagrams, and they say we don't have them. And we don't even understand them because it's very difficult to actually map the data flows. And I suggested them to request the data flows from the vendor, and the vendor refused to issue data flow diagram because for the intellectual property reasons. In that case, how are you going to investigate your system if you don't know whether this data flow is normal to the system or is it malicious? So you really cannot determine. And but more of these were data flows between the end devices. But also, it's very important to know the granular data flows on the individual devices, which do not exist at all. And this is one of the research questions I've been recently working. So, because once we start understanding what is happening with the data on the device, we suddenly can start enumerating attack vectors. Because in that case, we can understand where possibly the data could have been manipulated. So in that case, we can better understand how to look for the attacker on the device. Also, one of the challenge is that when something is broken, for example, a piece of equipment is broken, it's very difficult to understand what actually caused that breakage. So in this slide, we have, I will not go into the details, but because I'm slowly running out of time, but this is again one of my previous works. So it's possible to exploit, basically cause breakage of the motor by exploiting variable frequency drives, by basically changing the normal rotation frequency into the skip frequency, which is the damaging frequency to the motor. And it's actually relatively easy to do that without operator noticing it. So eventually the motor will break. Another way how to cause motor breakage is to hack the test on the digital test and maintenance equipment. So, for example, because this is a so-called handheld terminal. So it runs firmware, it has wireless, so it's basically you can exploit it. So what you can do then, you can show the good motor as being bad and actually cause a downtime because I will have to take it out and schedule the downtime. Or you can show the bad motor as being good, and then eventually the motor will break. But again, after the motor is broken, it's very difficult to determine exactly or accurately what was the root cause. Was it because of the test? Was it because of the bad rotating frequency? It's very difficult to determine. So, one of the largest, and what is still basically one of the, so we perform forensic investigation based on the data which we obtain process data which we obtain. And the problem is believe that the data is trustworthy. And especially cryptographers, they say that the reason why industrial control systems are insecure is because the protocols do not support encryption. So once we will be able to encrypt all of the industrial protocols, the problem is solved. The problem that it won't help, because the data can be actually manipulated at source before the protocol stack. Because the data is originated in the physical world, which is still not even IT system, not communication system. So basically, if we will be able to change the process data, manipulate process data before it become part of the communication infrastructure, then the insecure and damaging data will be securely delivered to the targeted applications. And this property of the data is called veracity. This term comes from the military domain, which actually determine the trustworthiness of the obtained information. And it first came in this, like, is the agent reporting true information or not? Can we take all the further decisions about this information, provided information? And there are so many ways how the data can be manipulated at source. It could be manipulated through the physics of the process. This is my ongoing work, and I already have a test bed, and I will be showing it within this year. I'll go a little bit quicker through this. The second is, for example, another way is just simply miscalibrating the sensor. Then the sensor will be already reporting wrong values, and the operators are making it only easier for the attacker, because it's now you push the entire calibration through some computer down into the sensors. So you basically can exploit a Windows machine and just already manipulate the calibration settings. One of the works which we've been showed last year or the year before, I don't remember, we've been basically forging sensor data right on the microprocessor, again, before the protocol stack, and the data were absolutely accurate, and basically no techniques would ever determine that, like, spectral analysis or Fourier analysis or entropy would detect that the signal isn't genuine. Another work which we've done actually this year, presented at Black Hat Asia, is that we've been generating specific, you can either generate specific analog signal from, for example, from PLC or from sensor, or you can change already analog signal on the line in such a way that two devices which consume this analog signal, they will convert it into the two different digital numbers. And that's only to be continued. There are so many ways how you can manipulate the data before the protocol stack. So this is a problem which really needs to be addressed, because you can't perform forensic investigation if you cannot trust process data. So, and this is what is like one of this is a good problem, because this is what something we all can understand, and we know this, that we never should trust our inputs. Only that in the industrial control systems, input validations refers to data content in the context rather to its formatting. So again, encryption won't help, because the data is already bad before it is becoming part of the communication infrastructure. And the data verification should take form of plausibility and consistency checks. So how it's done? For example, so there are a lot of, like, you should look at process interdependencies and understand the physics. So the laws of physics will help us to flag the inconsistent or implausible data. Like, for example, this is something has changed in here. And if you can see, there's two signals that really react simultaneously. If suddenly this or this will be absent, then we know that the signals will be forged. So, like, one of my works was that this is another plant. I was finding the clusters of correlated signals, and then I've been computing the entropy of the correlation. And as soon as one, again, I've done something. As soon as one or two or even all the signals in the clusters become basically spoofed, they will become incorrelated, and basically the entropy, basically we'll see the increase in the entropy. This similar method is actually also used in the by NASA to find the basically faulty or like broken sensors. And like, for example, another approach which I determined is that basically it's a good idea to establish trust. So again, you never can forge the physics of the process. So if you could take offline basically measurements, like samples of the physical process, and perform offline measurements, then just use those signals as the reference signals, and everything in the plant will be correlated to the samples which you take. One of the challenges of performing data validation is that if the attacker manages again to spoof data at very low level, like already on the sensor, which operate on milliseconds, there is really no time to validate, because even taking samples will always take 5 to 10 minutes. So for this one, I don't have really answer what to do right now. So I'm at the conclusion. At the conclusion, I actually wanted to explain you why cyber-physical forensics will actually eventually will evolve and why it will become important. So if you would like to jump on this topic, you will have jobs in the nearest future. So the point, like what is happening right now, that plant stakeholders, so basically stakeholders of industrial control systems, including governments, they're starting to understand that they are unable to catch up with the offensive hacking because those systems are living in the vacuum for generations, and suddenly they're all exposed to the attacks. So they just basically do not have even enough time to introduce all the necessary security controls, which we actually even still did not develop. So they're looking for the ways to transfer risks, security risk, by purchasing insurance. So plant owners right now really want to purchase insurance. So it is already possible to buy cyber insurance, which only covers like exfiltration, not even extortion, but exfiltration and some basically downtime caused by some, if you caught a virus. But they now want really to have insurance against cyber physical damage, like basically if you're losing money, if your product is again out of spec and so on. And obviously, like, okay, you will have to establish the baseline security, perform the, and then you basically, your premium will be for the residual risk, because you have to have a certain amount of security already there, like basically reduce risks to a certain level. But then you have really to have established at every single plant a trusted solution which would be continuously collect logs, so that later you would be able to determine that the downtime of the plant was it caused by the cyber accident, or was it just like normal breakdown? So, and again, in order to develop the solution which will be collecting these forensic evidences, we need to understand what to collect where and to develop tools. So the need is there. So probably, hopefully, the future of the cyber-physical forensic is bright. I wanted to acknowledge like all of my wonderful collaborators with whom I've been working over the years. And that is the end of my presentation. Thank you very much.
Time for a few questions. Yes.
Very nice talk. And I mean, it reminds me the challenge that automotive industry is facing today, because they are heading towards autonomous vehicles.
What?
I mean, automotive industry,
Yeah, okay.
they are heading towards the autonomous vehicles. And previously, the vehicle's security was through the key. And now it's a keyless entry. And then we are talking about the connected vehicles. And those connected vehicles will be in the cyberspace, and like different kind of challenges, but issues are more or less similar. And coming back to the same question that you initially highlighted on like unavailability of forensic tools available in that domain. Same challenge automotive industry is facing as well. So your comments on that side, I mean, how that industry can take advantage of some of the works that you are doing basically in this arena.
There is no easy answer to this. For example, every vendor, including Honeywell, for example, it is even illegal to reverse engineer firmware, reverse engineer our protocols. So even if you would like to monitor or like look inside of the transmitter, you're actually in trouble. So, and one of the reasons why the vendors are doing that is because, again, they're preserving their intellectual properties, because they don't want to share, because they invested so much efforts, like generations of efforts and money into developing their system. So they don't want it to like competitors to know like how this specific device is implemented so that they could copy paste. So unfortunately, yes, the offensive, that's why like again, you can't have data flows in the system because it's our intellectual property. So defenders are not having it easy. And unfortunately, you see there is this conflicting environments, like requirements or needs, which you absolutely cannot overcome. There is absolutely no way to overcome them. So also, it's all going to this, it's already kind of trying to implement that it would be illegal actually to hack your own car. So then you can't even look inside. And you see, like one of the problems, like again, like which actually make me so angry. Like my Toyota Camry was, the firmware of was updated automatically, because it's just pushed, and you can't basically buy a car without you have to sign up for like, yeah, I allow that firmware updates will be pushed into my car. But so basically, any attacker can push any firmware update into my car. And I am powerless, and I am not allowed to reverse engineer or control, like my car. I am also not allowed to control this process. So it's a brave new world, which we don't have answers right now.
Yeah. And on the top that, like performing forensic analysis if any incident happens, because in future, like if it's an autonomous vehicle and accident happens, so who is going to be the responsible for that?
This is one of the also problems. So why we don't still have like, also with insurance, so the problem is that because there is a vendor, there is software supplier, there is integrator, there is asset owner, there is somebody some security engineer. So when security incident is happening, who is liable? So the vendors tell that asset owners are stupid because they're not configuring devices in right way. Asset owner says that you sold me an insecure device. So because we still did not know how to assign the liabilities, we don't have insurance, and basically nobody is responsible.
Right. Are there any other questions?
He had a question.
There was one. Yes.
Yeah, thank you. Zeki Erkin from Delft. Thank you very much for this inspiring talk. I have limited experience in terms of hardware security, and I was collaborating with Riscure about smart meter, and it was impossible to get the specifications of the device, and even with the information we received, we saw that actually it was nonsense because it was not proper, there's no standard. Even the people who are expert couldn't understand, and it took not only, but it took 2 months to understand a rough idea, to have a rough idea about the device, and it was a very limited device. So what you're suggesting is a huge problem, but even one single device takes 2 months of time to understand how it works. So it's not possible for a research community even to do this. So what is your experience and what do you suggest? There's no way for us to get the firmware, there's no specification, and there's no support from the vendors, actually.
Yeah.
How do you deal with this problem?
Yeah. For example, also, one of the problems actually in this, because we have this huge amount of devices from different vendors. So for example, you know, like some people, some volunteers, especially like young people from the academia, like, oh, I will find some vulnerability and I will become famous and I will get a job. The problem is that you can't even, so if device is not belonging to a specific group, like it's not HP or it's not Honeywell, that you will not be even able to obtain the CVE score for your vulnerability. So so basically it's uncool or like useless for your career. So basically, therefore, like nobody would be looking even at smaller devices like meters and so on. So that is already the problem. There is no motivation. Or like bug bounty. Secondly is that, so I will say about solution like later. So with smart meters, yes, it's very difficult situation. Again, it's all proprietary. So when I was with European Network for Cybersecurity, we dealt a lot with smart meters. And for example, you would look at like, we will look inside of the smart meter, like, okay, so encryption. So we actually can do replay attack. Okay, so why is the reasons? Okay, so there is, the nonce is like all zeros. Okay, you message them like, okay, guys, you know, the nonce in the encryption protocol has to be random. Okay, we'll fix it. So they will return you the meter with a fix, and it will be a random number, but it will be static. It all will be always the same. Then you have to tell them, oh, guys, but you know, like it has to be always random at all times. So, and then the problem is that you only have that amount of time to actually test the meter. So eventually it will just, you can determine, like, find out, like, only that many issues. So, and basically then it goes into production and will be installed in our homes. Because, for example, in Europe, all homes has to have smart meters by 2020. So there is very little what we can do in this situation, and except is that we have to basically go to the roots and basically education. We have to be like, we have to introduce so basically no programmer should be allowed to go out of the university without like taking all security classes. A lot of practice, like basically, because you see, we teach that how about the encryption, but we do not teach about implementation of encryption. So we can only improve the situation with rising the educational level, because right now, like hardly any programmer took any security class. And like right now we've been hiring people from Georgia Tech, and at the interviews I've been asking like, so what do you know about secure software development lifecycle? Like, okay, good. So yeah, without those, we can't basically even start solving the problems.
Education.
Yeah.
Always. There was one question before, which is very, very quick. I'll take that too, but we're almost out of time.
Thank you for the presentation. I'm Harris from NYU. I see a paradox here. We say that from the academic perspective, we need to educate, and we have a problem because vendors design systems by obscuring the hardware. So, but I see a vendor logo on the slide. How does Honeywell helps into this problem? Do you plan to open source any designs, and what's the future from the Honeywell side, from the vendor side?
Again, you see, you have to see the company. So how Honeywell is specifically, we have a security, like we have a team which tests all of our like equipment or any piece of device, equipment, whatever. We have a team which will be testing them for like security, like functional tests. Basically, all the functions are there, and we have a team like of the pen testers. So we try to do our due diligence. And you see, for example, but again, like we cannot make it open source because, you know, like we invest money into design of those equipment, which is proprietary. So at least we're trying to do the due diligence. And for example, we are the first vendor out there from the industrial control space who really has an absolutely dedicated and separate from entire Honeywell group, which works for on the like cybersecurity for like industrial cybersecurity. So we take projects for our customers, execute security for them, and basically even like, let's say logically we are separate from our equipment. We don't like, basically we really just doing our job. So even if we will find something like with our experience systems, we report. We don't basically, so this is like this much we can do, but again, there is like legal constraints. Like I had to go through the legal, so I'm preparing the slides. I have to remove some certain graphics and text and so on. So industry has a lot of constraints.
All right, last question, very, very quickly.
So Bashar Nusebi from the Open University in the UK and Leroy in Ireland. So I'm an outsider to the field, so I was fascinated by the talk, but I'm trying to understand. I mean, a lot of the problems that have been described have been education, legal framework, practices. And I'm trying to understand if though, and you were saying that good security training is potentially the solution. But I'm trying to understand what the research problem is in such systems. Is it about the interplay between the digital and the cyber world and the fact that in fact that the techniques that we already have for security are ineffective for sort of analyzing this new attack surface that we have that's extended by having those two together? Or is it just that good security practice and education will solve the problem?
Oh, this is an excellent question. So You see, somehow, exactly for industrial control system, or let's say cyber-physical systems, IT people believe that if you reapply like network security, we solve the problems. And what they forget is that like security is not a fundamental science, it's application driven. We have specifically like web security, we have e-commerce security, we have GSM security, we have wireless security. You take the application which you're trying to protect, you understand the very unique security requirements and attack vectors on those applications. And then you try to develop security controls and like basically protections for that specific application. So this is the same what we have to do for industrial control systems and like in general cyber-physical systems. And this is where we still are struggling because suddenly, you know, like IT people more familiar with kind of with wireless and with web, they feel more comfortable. That is, and like engineered system is this where they absolutely have no knowledge, so they're afraid of them. They not even interested, they don't understand. So they try to solve the problems with IT, like as much as they can. But so basically the problem for this specific field, we still need to understand the field. And we need to understand like security requirements, needs. For example, even security properties in industrial control systems are not availability, integrity, and confidentiality. So, and then we need to like basically preserve those security properties with like appropriate security solutions. So this is what needs to be done. Therefore, like there are so many initiatives around the globe, like actually governmental, where they try to understand exactly to identify what are security needs of this field and basically formulate it so that we can start really actually solving the right security problems. So this is what needs to be done. And then secondly, education, what I meant is that just like basically, especially programmers, because at the end everything has to be programmed, or also engineers and managers. Yeah, we need to understand security, like basically be educated on security and how it is done. I've been teaching, so we had in my university international production managers, something. So basically people who will be managing operations like on the larger scale. And at some point, the university decided that they need at least to take course Introduction to Security. Our department was the most hated department in that university. And you won't believe, but after several years, they actually started boycotting and demanding to remove the class because they found it very difficult. It's just like, oh, it's out of our expertise and we don't need that knowledge. So eventually the class was, after like, I don't know, 5 years, the class was removed from that program because they've been like really demanding to remove it.
Yes, we need to stop here. Let us thank the speaker for the great talk.
So we'll have two speaks, then a coffee break. I will ask to the speaker to stick to the 20 minutes. And the first talk title is An Ensemble of One-Class SVM for Fingerprint Spoof Detection Across Different Fabrication Material. The first speaker is Wang Ding. Sorry for...
Hello. So, thank you for your attention. My name is Yaohui Ding, and I'm from the Integrated Pattern Recognition and Biometrics Lab in Michigan State University. So this work is titled as Example of One-Class SVMs for fingerprint spoof detection across different fabrication materials. So let's start with the background of fingerprint spoof detection problem and the challenges we have faced and the motivation for us to consider it as a one-class classification problem. Then I will introduce the proposed example of one-class SVM classifier, and the experimental result will show the advantage of this proposed method on detecting spoofs, especially for those generated from previously unseen materials in the training set. So background. Recent research have highlighted the weakness of biometric systems to spoof attacks, which are commonly realized by presenting a falsified or altered biometric trait to the sensor. For instance, it has been shown that some fingerprint system can be fooled by using a finger-like object that creates using commonly available materials, such as gelatin, silicon, Play-Doh, and so on and so forth. The example I'm showing here is from my colleague's work in Michigan State University. So basically, they use a standard inkjet printer to print some fake fingerprints, and they use them to successfully unlock the Samsung Galaxy 6 and the Huawei Honor 7 smartphones. So imagine that those smartphones are set up for like Apple Pay or Android Pay. And so it is potential to steal the user's payment card information using such a simple creation procedure of spoof fingerprints. It's very risky. And those experiments further confirm the urgent need of anti-spoofing technique. So in the past few years, there's a number of sensor-based or image-based anti-spoofing algorithms are proposed. The image-based solution in particular earn more attention because they don't require any extra hardwares, and they only based on the image that can be subsequently used by fingerprint matchers. So most image-based spoof detectors adopt a machine learning approach where a classifier is trained to distinguish the images of fake fingerprints from those of real-life fingerprints. But there are some special concerns associated with the use of binary classifiers in this specific context of spoof detection. The first one could be the imbalanced training set problem. We all know in practice, the training samples for the live class is very easy to obtain, but the training samples for the spoof class is pretty hard to obtain, which will lead to an imbalanced training set problem. But people will argue for some machine learning algorithms, they are very robust to this problem. So probably the second concern is more critical. Some spoof samples for the training are not representative enough for a binary classifier. In other words, we say the spoof sample, the training samples for the spoof class may not have the data corresponding to all possible types of spoofs. Especially we have so many available fabrication materials and the fabrication procedures. And recent work have shown the accuracy of a detector could be sharply degraded if the test set have some spoof fingerprints which are made using previously unseen materials. So some recent related work to this. In order to evaluate the efficiency of existing spoof detection algorithm, the biometric community have organized a series of computation. They call it the fingerprint liveness detection competition since 2009. And the convolutional neural network did outperform many benchmarks in this field. However, they do require a large number of training samples, just as some other CNN-based method. And there's no evaluation across different materials so far. Some other research use image quality-based measures to minimize the impact of fabrication materials. Still, they require sufficient spoof samples for their training. And the best performance so far was provided by these two works. They treat the problem as an open set problem, and they have a special design that firstly detected the spoof samples to detect whether the spoof samples are made using unseen materials. If yes, some parameters of their detector will be automatically updated to adapt this unseen material. That's their solution, and they have the best performance as reported so far. Our motivation. So the mentioned concerns motivate us to consider the spoof detection problem as a one-class classification problem. So the idea is simple. Instead of you learning the concept of the spoof class, the goal of one-class classification is to learn the concept of the live class and use this learned concept to reject all the spoofs, no matter what materials or a method are used to create them. However, it actually makes the problem even harder. The table here compare the detection accuracy on spoof samples using conventional one-class SVM and binary SVM. We can see the one-class SVM performance is totally unacceptable. And there are some reasons. Like we all know, the one-class SVM is more likely to overfit the live class. Imagine we have a separation line between two classes. If we use a binary classifier, we're going to push this line from both sides. But if we consider the one-class SVM, we only have training set from one side. So we push the line, how? So it's a little harder than one-class SVM. And another possible reason is the feature space. Like I showed here, the feature I used, like the LBP, LPQ features, they are commonly used in the field of fingerprint spoof detection. But they are good for, they are designed for binary classifier. And now our goal is to capture the concept of the live class. So probably it's better to use multiple feature sets instead of limit this concept to one specific feature space. The proposed framework. So we make three major changes for the one-class, conventional one-class SVM. First, we use multiple kinds of features, and we know single one-class SVM does not work. So we need some strategy to aggregate those weak one-class classifiers together. The third one is optional. So we have some spoof samples available. Suppose we have some, and we don't want to waste them. Probably we need some way to use them and try to improve the accuracy. So the framework, I will go to this later, part by part. The main contribution of this work. So it is the first successful one-class classifier to deal with the spoof detection problem. And the proposed method have a comparable accuracy with state-of-art algorithms, but only live samples are predominantly used. And we also noticed the accuracy on detecting spoofs are pretty consistent, regardless of what fabrication materials are used. Plus, we provide a way to add spoof samples to the one-class SVM and improve the accuracy. Okay, go to some the theory. Among a number of one-class classification approaches, one-class SVM is very popular, one popular technique. And the main idea of one-class SVM is very similar to binary SVM. The figure on the left actually show the data from the input space are projected to a higher dimensional space using two different one-class SVM. approaches. One is hypersphere-based, is the upper one. And one, we call it support vector data description. And another one is a plane-based. So we're going to focus on the hypersphere-based approach proposed by Tex and Dwayne. So simply speaking, the idea is to minimize the volume of the decision hypersphere that contains the training data from a single class. So the first formulation here is trying to solve this quadratic programming problem. And still some. Okay, fortunately, the left part works. R is the radius of this hypersphere. A is the center. C is the select variable, which allowed the sum of the data fall outside of this hypersphere. And the very important parameter is this new. It is a user predefined regularization parameter, and it controls the trade-off between the size of the hypersphere and the fraction of training samples falling outside of the hypersphere. So in our case, it's actually new is the fraction of training samples that are classified as spoofs and being rejected. So I won't go to the detail about how to solve this problem. We can go to the paper to see more theoretical part. Okay, I'm going to focus on three proposed change for the conventionally one-class SVM. So firstly, each one-class SVM is independently trained using a different feature set. So the aggregation strategy could be very simply using the majority voting. It's straightforward, but based on our observation, the alternative method, the least square estimation-based weighting, will always perform better. And we estimate the weight vector W for each feature space. And the main idea is the higher weight it will assign, the higher weight a feature space will be assigned if it has a higher accuracy. And the proposed global regularization, after we have a initialization of the LSE weight vectors, we're gonna adjust the global regularization parameter new in step 3. And the idea here is to, firstly, we have a starting point of the weight for each feature space, and then we try to find the optimized value for this volume of each hypersphere. After step 3, we gonna re-estimate the LSE weight vectors to Okay, so far we didn't use adding spoof samples in our proposed method. Now, based on the original author of the one-class SVDD method, they actually offer a way to use negative examples. And in our case, the spoof samples are added in as a validations phase. And we try to separate this phase to the training phase. And we try to highlight those spoof samples are not necessary for this method, but it can be used to improve the method. So by adding spoofs, the regularization parameters will be readjusted again. And we're going to use a slightly different metric to optimize this value, this parameter. Experimental result. The database, we use the LiveDeck 2011 database. It is from the competition in 2011, and it have images from 4 different sensors, And corresponding to each sensor, there are 1,000 live and 1,000 fake fingerprint samples in the training set, and the same numbers of samples, but from different subjects in the test set. So in order to evaluate the efficiency across different materials, the protocol used in this 2014 paper are carefully followed. And the two more performance metrics are designed as here. Okay, baseline. We proposed 3 different baselines to compare this, to compare with the proposed method. First, the baseline is the automatic adaptation detector, as we mentioned before, and compare the table, the column 1 and the column 4 in the table. It can be noticed that the average detection accuracy are comparable between baseline method and the proposed method. And the proposed method actually show advantage on detecting fake fingerprints made by previously unseen materials in the training set. Furthermore, the performance of baseline 2 and 3 are listed in column 2 and 3. So basically, we implement the feature level fusion and the LSE weighting aggregation to the binary SVM classifier separately. And we find the modified binary SVM still didn't overcome the inherent weakness, as we point out, for the binary classifiers. And so far, no smooth samples are used. If we use the validation, we have a validation part. We're going to improve this performance a little bit, like around 2%. The possible reason for those improvements is the smooth samples further tighten the decision hemisphere from the outside of this hemisphere. And the smooth samples are more likely, to fall outside of this hemisphere. And this table is much simplified from the one we posted in the paper. So if you need more details, please go to the paper. And consistent across the materials. In this experiment, we test the consistency on different fabrication material. And in the left figure, the x-axis is different combination of training materials used in the baseline method. Please note, when the materials are used in training, it won't appear in the test part. The y-axis is the equal error rate, and it can be noticed that the proposed method have a similar standard deviation on error rates when we test it on different materials. And the average accuracy is comparable with the baseline method. Okay, summary. In this work, the smooth detection problem is considered as a one-class problem. And instead of learning the concept of smooth class, the proposed method successfully learned the concept of the live class and be able to provide a comparable accuracy with the state-of-art algorithms. But very much fewer smooth samples are required. Future work. So all the features in this work are previously extracted for binary classifiers. So although there's no constraints for proposed method to use what kind of features, the performance could be further improved if some more efficient features are selected from the one-class classification perspective in the future. I guess that's it.
Thank you. We have time for one or two questions. Yes?
Okay, just a quick question. It appears that most of the features that you used to distinguish spoof fingerprints for the original ones were visual.
Yeah.
Yes? So are there any other works where people try to take into account other factors, like maybe the temperature of the fingerprint,
right?
Things like this. Is it?
Yeah. As I mentioned, there's two big categories, sensor-based and image-based. All we focus on is the image-based. The sensor-based, they can test like the pulse, boom, 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 and the temperature. Yeah, even the sweat point. A lot of different features are used in the sensor-based method. Yeah.
Okay, are these two approaches combined? I mean, both image-based features and sensor-based features?
Combine. To my best knowledge, I don't think there's much work on the combination of these two kinds of technicals. Because for the hardware-based method, always use hardware. And when they focus on the hardware, I don't think the image processing part is very strong. I was thinking, yeah, that's based on my understanding. So if I'm wrong, sorry about it.
And we have another question here.
Thank you. A quick question. Notice by add some spoof records, you cannot increase accuracy rate. I notice you add 50 records. Just wondering, does it help if you add more? So and how do you
Thank you so much for asking this question. It mentioned in the paper, we actually increased the number of samples we used from 0 to 400. And yeah, we can see the trend. It's increased. And the thing I didn't put it here because from the experimental design perspective, I was thinking every time let's consider one major factor. If we try to say, okay, we increase the samples we used, then the performance could be, impacted by this increasement of the sample size, not about this classifier. So let's focus on this classifier at this moment. So.
Okay, let's thank the speaker again and go to the next talk. We're gonna switch from fingers to faces with so a talk named on the usefulness of color for kinship verification from face images. The speaker is Hello Cine? No, sorry. Okay, sorry. Ben Moore Hadid.
Good morning, everyone. It's my pleasure to be here. Our talk is about the usefulness of color information for kinship. I am the last author here, so this is work by my students. I will try to keep the presentation very short and very clear. And if you have any questions, so I am trying to skip the details for later. So if you have any question or something like that, so I will be very happy to discuss that with you. So I'm coming from the University of Oulu in Finland. So I am coming from the top north here. This is Europe, so I'm coming from the top north here. So it's very funny or very fun to be here in the desert. So anyway, yeah, this is so I'm coming from, this is from Oulu in Finland. And a few days ago, it was like snowing minus 40 degrees, and now it's a desert here. It's really very fun. Anyway, I invite you to come to Finland if you have time at some point. And greetings from the Santa Claus, by the way. Now let's come back to the business. So my talk, it's about the usefulness of color information in kinship. I don't know if you are familiar with kinship or not. But the idea of kinship is, briefly, giving two images like this. The idea is to check if there is a kin family relationship between these two images or not. So it's kind of a binary problem. So you have two images, and your task is to automatically detect or recognize if there is some relationship, family relationship. For example, here, is this one the father of this girl or not? So so this is just like, if you are given these two images, so you should just decide if this man is the father of this girl or not. I'll let you guess in this case, if the answer is yes or no. You can decide. Yeah, the first thing which comes in mind is why do we need to do that? So in terms of applications, so we can see, for example, finding missing children, for example, or there is also there are also applications in image annotation and social media analysis. Let's play a game for a while. Who thinks that this guy is the father of this girl? Yes, no? Can you guess? Yes, no?